Okay, let's calc for lecture 14, and that's orthogonality. Now, orthogonal is like perpendicular, so it's the same as perpendicular for us. Now, perpendicular is applied to like in geometry, we say something is perpendicular. Orthogonal is more, say, mathematical, or more scientific, more abstract, say. But anyway, so we had a nice inequality, the Cauchy-Schwarz inequality, which was u dot v is less than or equal to u times v. This, if I remove absolute value here, I will get u dot v is less than or equal to u v bigger than or equal to minus u v. Okay? If I divide by u v, assuming that none of them is 0, not 0, assuming none of them is 0, otherwise we just get 0. So if I divide by this, I will get minus 1 less than or equal to u dot v u v, and this side 1. So this quantity, this thing here, is a number between -1 and 1. What else is between -1 and 1? Sine and cosine. So, since cosine is much nicer than sine, but there's a reason. But we left this to define something. So the definition, given vectors u and v in Rn, the cosine of the angle between them is defined to be cosine theta is defined to be this thing, u dot v over u times v. Okay. And this is well defined because of this fact. Well defined means what? If I define cosine of something to be something, then that definition should comply with properties of cosine, which is cosine theta is a number between -1 and 1. And by Cauchy-Schwarz inequality, this thing is between -1 and 1. So it can be assigned to cosine of something. But this is not just out of thin air, no. In R2, this is in fact cosine theta. This in R2 will give you cosine theta, and also R3. Well, R2 is more important because we can visualize, or in fact draw some pictures on this whiteboard, which is R2. Okay, so what does orthogonal mean? Orthogonal means the perpendicular, right? So let me erase this. So I have orthogonal and perpendicular over there. So perpendicular or orthogonal means that this is 90 degrees or pi over 2. What is cosine of 90? 0. Cosine of 90 is 0. So if cosine of some theta is 0, or cosine 90 is 0, how should I say that? If I can relate this to the definition of cosine theta for vectors in Rn. So if cosine theta is 0, this is if and only if this is 0. But the denominator is not 0. So it is u dot v is 0. Right? So this, in a sense, if we can visualize something which we can't, but we just say there is something called angle between two vectors. And if this angle is 90, then its cosine is 0, which implies, so it is if and only if, the dot product of the two vectors is 0. So we take this to be definition of orthogonality. So we define this as definition, or we take this as definition of orthogonality. Definition: U and V or N are orthogonal, and we denote this by this, which we might have seen in. There are other ways to denote it by this. If and only if U dot V is 0. So there is no kind of, it's just that's definition. So if that happens, then we say that they are orthogonal. So let's see what we can get out of this. Let me go back to Carl's algebra and use this thing to develop certain things. Lines in R2. You might remember the line was like this, mx plus b. But there is something, it's okay, well, but there's, this gives me equation of a line as a function. But I'm just talking about the line as a geometric object. So there is something wrong with this. You cannot write equation of a line perpendicular to the x-axis. But other than that, you can write equation for any other line. But there's another one. There's another one which is more important than this, and that is ax plus by equals c. Or, like I guess in your textbook, it writes it like this either way. You can either write c here or on the other side. You might have seen this more than this one. But anyway, that is equation of any line. Equation of any line. So this also includes something like this, x equals 5. That is when a is 1, b is 0, c is 5, right? But here we cannot, x equals 5, what is it? It is y equals what? So this is more important. Now, let me use this, and let's say I want to find the equation of a line that goes through point x0, y0, and is orthogonal to vector v, which, let's write it f, because that is the one that is usually used for this kind of vector n. And this is AB. Okay? So, find the equation of a line. So, this is a problem. Find an equation for a line that passes through point x0 and y0 and is orthogonal to n, which is a, b. Okay, so let's look at this the statement. It is asking for an equation for a line, well, and gives you some information. Now, what is equation? Equation of an object means, well, this object is in some Rn, right? Equation of that object means finding a relation or relations. It might be several equations. A relation or relations between the coordinates of a generic point on that object. So, well, let me do it here and then I will explain again. So, generic point. So, you take a generic point, say point xy here, and then you have to find a relation or relations between the x and the y. Now, if I had something in Rn, it would be x1, x2, x0 up to xn. I have to find relation or relations between them. And those relations should include some equalities. That's why you see equation, which comes, and equality, they come from the same thing. So it should include some equalities, or equality, or just one. Okay, now this is how I do that. This vector, consider this vector. Let's call this point A, and let's call this point B. And also I have this vector here. So this is point A and point B. And AB. AB is what? Vector AB. Vector AB, remember it was B minus A, right? As vector, but they are not vectors, but anyway. So that was in fact x, y minus x0, y0. So that is x minus x0, y minus y0. And I know that by, it says passes through this point and is orthogonal to this. Orthogonal means any vector on this line is orthogonal to n, any vector. So if any vector here is orthogonal to n, then this AB should be orthogonal to n as generic. This should be orthogonal to n. Orthogonal to n means this n dot AB is 0. N dot AB is 0. Well, what is n dot AB? N dot AB is n transpose times AB as a vector. So it is A comma B. Sorry, this is just a matrix. So it is A B times this thing. X minus x0, y minus y0. And this should equal to 0. Okay? So, let me erase this and continue on here. So, dot product, it is this times this plus this times this. So I have A times x minus x0 plus b times y minus y0 equals 0. Well, we can stop here and say, okay, that is the equation of this line. This is a relation between x and y that involves an equality. You see, it is something times x minus x0 plus something times y minus y0, and that equals 0. So this is done. But we can just put it in a much nicer way, at least something which resembles what I erase that. So let me rearrange this thing, ax plus by, and I can move this thing, ax0 plus by0. Isn't this familiar? Ax plus by equals something c, right? And the c is this. And remember, x0, y0 are given. A and b are given. So this side is given. This side is but this side A and B are given, but X and Y are coordinates of a generic point on this line. So this is similar to the other equation which I wrote for you here, and I said we use look at this. So it's like that. So by using this idea, or the ideas from vectors in R2, R3, whatever, I came up with, this is R2 in fact, I came up with an equation for a line, and this equation resembles that equation that we had from college algebra. So let me erase this and give you an example. Let me erase this and give you an example. So this is an example, in fact. I will give you just one example. Find an equation for a line that passes through point, well, this point is almost 1, say, maybe 2 and 5. So let's say this is 2, 5. And this one, I would say it is maybe 3 and 2, something like that. And n is 3 and 2, in this picture. 3, 2. Okay? And so, line that passes through 2, 5 and is orthogonal to orthogonal to 3 and 2. Okay. So, what was the formula? The formula was n dot this vector. Vector was x minus 2, y minus 5 equal to 0. And so that is the vector over there, 3, 2 times x minus 2, y minus 5 is 0. So I have 3 times x minus 2 plus 2 times y minus 5 is 0. And that gives me 3x plus 2y. 3 times 2 is 6, 2 times 5 is 10, equals 16. So that is a nice example that uses the orthogonality idea, and that n is called normal vector to the line. Well, we usually don't write lines like this. Maybe that y equals mx plus p is more useful than doing it like this. It is too abstract. But anyway, now if I give you equation of a line, well, let me write it as another example. Example, find a vector orthogonal to the line this. Okay. So let me. Oh, this is okay if it stays here. So what is it? It's very simple. When you look at this, the answer is minus 5, 4, minus 5, 4, down. Okay. So orthogonal to that is simply minus 5, 4. Now let's look at some special examples. So if I give you y equals say 10, what is orthogonal to this? You write it in this format: 0x plus 1 y is 10, so n in this case is 0, 1. If I say x equals negative, say 8, then this is 1x plus 0y equals negative 8. So n in this case is 1, 0. This n is in fact the j, and this n is the I, which makes sense. I is this, is orthogonal to any line like this. J is this, orthogonal to any line like this. This is a horizontal line, and j is this way. So j is orthogonal to any horizontal line. Okay, so this is how we find the equation of a line using normal to the line. The one that you have seen in college algebra is it can be extracted from this, but that depends on the slope of the line. That m is the slope of the line. So let me erase this, and this is not anymore college algebra. The next one is planes. Equation of the plane in R3. So problem, find an equation of a plane that passes through point P0 given by x at 0, y at 0, z 0, and is orthogonal to n, a, b, and c. So find an equation of the plane that passes through a certain point and is orthogonal to this. So this is called normal to the plane. This is normal to the plane. Okay. So let's see. So this is my plane, say, and this is the x, y, z coordinate. Do you see this? X, y, z, and say this is point P, 0, say. P0, this one. And I find a generic point P here. So that is a generic point. Let me extend this so it doesn't interfere with this. So I have P, P0, and this is a vector, and this is n. So I know that n is, you can even take this as definition of a plane in R3. A plane is a set of points P such that P0P is orthogonal to n. So n is orthogonal to P0 or P0P. This means that n dot P0P is 0. So n dot is in fact, n is A, B, and C. P0 minus P. Let's say P is P has coordinates x, y, z. That is the generic point in the plane. So that is x minus x0 x minus x0, y minus y0, and z minus z0 equals 0. So this gives me equation of a plane using normal to the plane, x minus x0 plus b times y minus y0 plus c times z minus z0 is 0. Okay, so that's the equation of a plane. So, let me give you an example here. Find an equation of the plane that passes through a point. Let's write some points here and some vector, something here. Point, say, 2 minus 3 and say 5, something. And the vector is, say, negative 1, say 2 and say 8. Okay, so P0 and N are given, and this is what I have, and that's the formula. Let me erase it. So it's very simple. It is A minus 1 times x minus 2 plus 2 times y minus 3 plus 8 times z minus 5 equals 0. Okay, so I can expand and make it simpler, and that is minus x plus 2y plus 8z. The constant here is minus is plus 2 here, and 2 times 3, this is 3 plus 6, minus is plus, and minus, and that is 40. So that's 40 minus 8, so I have minus 32. Well, I can write the 32 on the other side, and this resembles equation of a line in R2. Okay, so that's how you find it. It's very simple. It's important to understand what's going on. If you have taken Calc 3 before, you can connect with this, you have seen it. Otherwise, it's good if you take Calc 3 after this class, so you know something about planes using this idea. Okay. So let me erase this thing. Projection. Again, projection is used in physics and engineering a lot, and we also use it. It's extremely important that, or maybe we do not touch it in this class. But if you ever study, say linear regression, for example, that is related to projection. Anyway, so. What is projection? So let's say in Rn, we are in Rn, and we have a vector v, say, and another vector w, and we project it. Project means just draw like a plane or something perpendicular, so we get something like this. So we get this vector in direction of v. this is the magnitude of the projection. And the vector is called projection. So the vector is denoted by projection of W in the direction of V. Okay? So that's projection of W in the direction of V. And now let's see what we have here. First of all, the question is, can we find the magnitude of this thing? Well, let's look at this. We have, if this is theta, say, so that's like the angle between these two vectors. And we have a triangle here. So the magnitude of this projection, well, let me write it OH. And this is A. So OH, in fact, is OA times cosine theta. From early trigonometry, OH over OA is cosine theta, so OH is OA times cosine theta. But OH in our language is the magnitude of this. Magnitude of this projection. OA is the magnitude of this guy, which is in fact vector W. So that's vector W times cosine theta. But what is cosine theta? We have two vectors here. Cosine theta is, we know that is V dot W divided by V W. Okay? V dot W divided by VW. Now, when this is a constant, this is a constant, so they cancel out, and I will end up with this. I can write W first. It is W, or which one? Yeah, W dot V over absolute V, right? But this V over absolute V is in fact a unit vector in this direction. So U times absolute V is a unit vector in the direction of V. Okay? So projection is in fact W dot a unit vector in the direction of V. So let's write it here. Magnitude of projection. Which one I have? So let's start here. So magnitude of projection, or magnitude, or no, that's magnitude of projection of W over V is W dot U, or U is a unit vector in the direction of V. And which unit vector? No, because we have two. So the one which comes, which the constant is this, not the negative one, this one. Okay? So if I dot W with a unit vector in this direction, or that specific unit vector, I will get this magnitude. Okay? So, what is the vector? A vector in any direction, if I have its magnitude, is that vector times unit vector, the magnitude times unit vector in that direction. So the projection itself, if that is the magnitude of the projection, then the projection itself is simply, the projection itself is simply the projection, the vector is simply the magnitude times unit vector. And this times is just a constant times a vector. Okay? It's a constant times the vector. So to find projection, you take two steps. Well, yeah. So let me write down the steps here. Yeah, I can erase this thing and write it here. So that's like an algorithm or something you can call it. 1. Find projection of W along V. Find a unit vector U in the direction of V. To the magnitude of this projection is W dot U, and 3, the projection itself is its magnitude times unit vector in the direction of the projection. So these are the 3 steps. If you take these 3 steps, you find projection. There is some big formula in the book. I do not suggest that, because if you need this at some point, I can't remember that, to be honest with you there. But I can remember this procedure. Do this, and you find the projection. Let me give you an example. Find projection of W on V, where let's say W is 2, -3, 5 again, something like that, and V is say negative, say 5, 2, and say 1, something like that. Okay, so 1, I need the U. U is 1 divided by V times V. What is absolute V? Absolute V is 1 over 5 squared is 25, 4, 29, 30, right? 5 squared and 25 plus 4 plus 1. Times the vector itself, -5, 2, and 1. 2, the magnitude of the projection is W dot U, so it is W or U dot W, no difference. So it is this dot this. Well, since you don't like that, let's write it like this: 2, -3, 5 times this. But I can write this 1 over square root of 30, that is like a constant. We can write it outside. So let's write that first. Constant can be written anywhere. Where is 2 minus 3 and 5 times -5, 2, and 1. So it is 1 over square root of 30, and 2 times 5 is -10, -6 plus 5. 10, -6 plus 5, that is 16, 11. So that is in fact -11 over square root of 30. Okay, so the magnitude is 11 over square root of 30 minus 11 over square root of 30, and now the projection itself is 3. The projection as a vector is simply this times U. So it is -11 over square root of 30 times 1 over square root of 30, this vector. 2 and 11. So this square root of 30 is what they multiply, and you will get 11 over 30 times this. So the projection is this vector. You don't have to bring this inside. You can write it like that. It's okay. So that is the story of projection in a certain direction, and so let me erase this, and there are two other things here. So I can do PITH A. So this is in fact if I have two perpendicular vectors, say in Rm, so U and V. Okay, so if this is U this way and V this way, this is U plus V. I want to say if this squared is this one squared plus this one squared. So I ask this question: is U plus V squared, is this equal to U squared plus V squared if U is orthogonal to V? So if they're orthogonal, the question is that, say, does that apply? So let me write this. So this is U plus V squared. We know that this is U plus V dot U plus V, and we know that when I foil it, I will get this U squared plus 2 U dot V plus V squared. But I know this is 0. Orthogonal means this. U dot V is 0. Right? So this is 0. So this equals U squared plus V squared. So yeah, it also, in fact, we have the same formula or the same equation in Rn in the Pythagoras theorem. Next is distance of a point from a plane. So let me erase this thing and discuss that distance from a point to a plane. From point, say, P x 0, y 0, z 0 to plane ax plus by plus cz plus d equals 0. Okay, so plane equation of a plane looks like this: ax by cz equals 0 plus d equals 0. And what is normal to the plane? Normal, well, we need the normal to this plane. So let me draw the picture and then explain. So this is the way we find it. So we have this P somewhere, and we want to find this distance. which is perpendicular, right? This is what we do. We find a point like P0, well, let's call it P0. P0, but that's x0. So we just look at the one point here, point say P here, with coordinates x, y, and z. Then if we find projection of P0P onto n, projection of this onto n. So if we project this vector onto n, the magnitude of the projection is distance, right? The magnitude of this projection is distance. So let's do it. So we need the projection of the magnitude of projection of P0P on n. Well, we know that what that is. It is in fact this equals to P0P times a unit vector in direction of n times 1 over n times n. Right, this is done. So 1 over, and what is n? N, remember, n is this. A, B, C. Right? So if the equation of a plane is given to you, coefficients of A, B, X, Y, and Z are in fact A, B, C. So PP0 is, well, let's write it. So that is in fact X minus X0, Y minus Y0, Z minus Z0 times n, A, B, C, and everything is times 1 over absolute n. Well, I mean, magnitude n. So, and since we want distance, we put absolute value here. Because this might give me a negative number. So we need the absolute value of this because we want distance. It might be negative or positive depending on some directions. And so we need absolute value of this thing. So if I multiply, I will get this. So this times that, where on top I have absolute A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0. And the denominator is simply square root of A squared plus B squared plus C squared. That is magnitude of n, right? So this is distance. This is distance, but we can, because both x0 and x are given to me. Both x0 and x are given to me. Well, I should have taken this to be x0, that's okay. So I have this thing. So I can write this in this form. I can flip this thing. In fact, I could have written P0. Right? P0, not P0P. So if I flip all of them, it's like multiplying all of them by x by negative. So I have A x0 plus B y0 plus C z0, and I have minus ax minus by minus cz, and the denominator is square root of a squared plus b squared plus c squared. Now this guy here is d, in fact. This guy here is d. You see, it's here. This guy here is d. So the equation becomes this version right here. The equation will become a simple one. It's like equation of the plane, in fact. So it becomes this: ax0 plus by0 plus cz0 plus d over this. So that is a distance from a point to a plane. And there's also distance between two parallel planes. Let me distance between two parallel planes. Let me discuss that too, and we'll finish this lecture. Distance between two parallel planes. So we have planes plane 1, plane 1 has equation d1, and plane 2 is ax plus by plus cz plus d2 equal to 0. Parallel planes have the same normal. Parallel planes have the same normal, right? So that's why the normals are the same. So if this is one of them, and this is the other one, so it is in fact, if I take a point here, it is the distance from this point to this plane. So a point on plane 1, say, from plane 2. So this point is that generic point x, y, z, for example. And if you write down that formula, you will see that it becomes the distance, this d becomes, you can take a look at the book because I'm out of time here. So this will be d, one of them I can remember, d1 minus d2 or d2 minus d1, no difference, over a squared plus b squared plus c squared. Okay, so the distance is in fact, and you can use that formula for this one, and it immediately you get that. So I'm done with this section, the orthogonality, and I will do another section next time. So see you next time.